Next is ionization enthalpy. When we talk about the periodic table, how ionization enthalpy varies across a period. Means when we are moving from left to right. Across a period means left to right in the periodic table. So when we move from lithium to fluorine, so this is an example. Lithium is on the leftmost side and fluorine is in the on the rightmost side. We are not considering noble gases. Okay, so whenever we are talking about the trends, we are not talking the noble gases because these have fully filled configuration and properties are entirely different from other elements. So in second period, lithium to fluorine. So what happens successively an electron is being added here. So because atomic number is increasing by one, number of protons also increasing. So you have three here, 4, 5, 6, 7, 8, 9. So effectively, the size is decreasing. Why? Because the force of attraction is increasing. 3 protons means plus 3 charge, plus 4 charge, plus 5 charge, like this. So because force of attraction on the valence electron is increasing, that's why size decreases. So the probability of finding an electron in the region will be shrink. So it will shrink. So that's why the radius will decrease, size will decrease in this case. There are few exceptions about ionization enthalpy. So how ionization enthalpy is related to this? Because force is increasing. So the attractive force increases in this direction as shown by the arrow. So it means it will require more energy to remove the electron. So for example, this electron will be bound with greater force by the nucleus. So it will require more energy to get removed. And ionization is removal of electron from the valence shell when the atom is in free gaseous ground state. Okay, it is not attached to any other atom. It is in gaseous form, and it is in the electron is in ground state. It means the ionization enthalpy increases across period. It will require more energy to remove the electron. There are exceptions we will be talking about in a few minutes. Okay. So thus, across a period, increasing nuclear charge outweighs the shielding also. So there is shielding also when we say that we have greater number of protons, there will be greater number of electrons. Okay, so greater number of electrons will result in shielding also. Means the interelectronic repulsion will result in shielding also. But shielding will be outweighed by increasing nuclear charge. What I am saying? I'm saying that in this case, if force of attraction increase, because there are two electrons now, there will be interelectronic repulsion. So interelectronic repulsion will try to repel the electrons from one another. Interelectronic repulsion will lead to increase in size. Now force increased, this will lead to decrease in size. But interelectronic repulsion is of very, very small magnitude. The force of attraction is much greater than the interelectronic repulsion. So ultimately, the increased nuclear charge outweighs the shielding. Hence, size decreases, force of attraction increases, and the electron is more tightly bound with the nucleus. It will require more energy if we move from left to right. Now, ionization enthalpy down the group, if we move from top to bottom, then what will be the ionization energy? Here, just a new shell is introduced. So if you talk about the second period, third period, fourth period, second period means valence electron will be in second shell. Third period elements will have valence electron in third shell, and so on. So because one shell is introduced, the electron becomes far away from the nucleus. Why I am saying far away? Because if you remember the formula, okay, what is there? N square. It means if I am just moving from 2 to 3, it will not be just double. It will
The
be
number of
rather,
orbitals.
yes, N is number of orbit. Okay. So 2 square will be 4 if I am having second shell. Okay. So R2 will be 52.9 into 2 square, that is 4. However, R3 will be 52.9 into 3 square, that is 9. So it is more than double. And R4 will be 52.9 into 4 square, that is 16. So it is not triple. From here, double, triple, no, rather it is 4 times. So the size increases a lot if we move from lower shell to higher shell. So because size increases substantially, the electron is far away. The electron becomes far away from the nucleus, and it becomes easier to remove the electron. So electron is not tightly bound, as tightly bound here as it was here. Electron is not as tightly bound here as it was here. So it means when we move down the group, it requires less energy to remove the electron. The electron is far away, force of attraction is less. So down the group, ionization enthalpy decreases. Now there is uh, some common phenomenon which you will remember. Most of the times, if anything increases across period, it will decrease down the group. If it decreases across period, it will increase down the group. And there is a table there I will show you. So ionization enthalpy increases across the period, it decreases down the group. That trend will be followed in almost all the properties. Whether we are talking about ionization enthalpy, whether we are talking about electron gain enthalpy, whether electronegativity, whether size, that is radius, in all these, this will follow. In one direction, if it increases, in other, it will decrease. So in this case, increase in shielding outweighs the increasing nuclear charge, opposite of that. Why? The reason is the shielding is now much more because there are much more electrons present inside. Here, if you see, the electrons were these many. You count total, okay, 10. 2 plus 8, 10. But for this, how many electrons are there total? 18 electrons. So 18 electrons will provide much more effective shielding as compared to the force of attraction. So you might say that there's huge difference in atomic number. For example, sodium has atomic
Yes.
number 11 and potassium has atomic number 19. So many more protons plus 11 charge here, force of attraction, and plus 19. So it should rather be smaller than the previous ones by this logic. But first logic we need to remember, this is addition of an addition of a shell itself. One whole shell gets added. So that's why huge difference in size. Second, now there are much more electrons present inside which provide significant shielding. So now these electrons which are there, these electrons provide significant shielding. These repel each other too much. There are too many electrons, and that's why size increases. And because the valence shell is now very large, the force of attraction is less. The nucleus does not have much effect on the valence electron. Now the anomalous behavior, and questions will appear mostly from exceptions and anomalous behavior. Anomalous behavior in ionization enthalpy across a period. The first one is beryllium versus boron. We have these elements in second period. Okay, lithium, beryllium, boron. After that boron, we have carbon. Okay, 6, 7, 8, 9, 10. So this is an exception. We say that the size across a period decreases, force of attraction increases, hence ionization enthalpy across a period increases. This is something we have talked about. But if this is the case, then after lithium we have beryllium, then we have boron, carbon, etc. Then ionization enthalpy should increase in this sequence. However, boron has lower ionization enthalpy than beryllium. Okay. So here it increases. It should increase here further, but it decreases and then again increases. Why this is so? That is the anomalous behavior we are going to talk about. For that, we need to understand this graph, why this is so. Okay. Understand the reason now. We have lithium, beryllium, boron, carbon, lithium atomic number 3, beryllium 4, boron 5, 6. If I write the electronic configuration for lithium, it will be 1s2, 2s2, oh sorry, 2s1. So 1s2, 2s1. It will be 1s2, 2s2, 1s2, 2s2, 2p1, 1s2, 2s2, 2p2, like that. Now see the difference. The difference is here there is no significant difference. The electron, valence electron goes in s orbital of second shell. Here also valence electron goes into s orbital of second shell. But here the valence electron enters p orbital. And if this is the second shell, okay, then the 2s orbital will be like this. 2s will be like this. And 2p size is much greater than s. Now, difference in beryllium and boron will be that in beryllium, the electron will enter here in 2s. However, in case of boron, the electron will enter here in p, 2p, not 2s. In 2p, the electron for most of the time will be farther from nucleus. As compared to 2s electrons. It means there will be greater shielding effect by 2s electrons. There are 2s electrons here. These two are 2s electrons, these two in 2s orbital. These will repel the 2p electron because 2p electron is in outer region. 2s electrons cannot go beyond the 2s region. So this is one reason. Means greater shielding will be there for this electron. It means the effective force of attraction will decrease. So for 2p electron, effective force of attraction will be less than 2s electrons. Secondly, it is more difficult to remove electron from the inner region. This electron, if I consider, okay, it is in inner region of the atom. So to remove this electron, it will require more energy. Hence, will require greater energy. So two reasons I am talking about. First reason I am talking about for boron. For boron, the electron will be in 2p. And 2p is bigger size, hence inner 2s electrons, these are inner 2s electrons. These will provide shielding, these will shield the outer electron. So force of attraction will decrease, hence it will be easier to remove this electron. It will require less energy, means less ionization enthalpy. Moreover, for 2s electrons, these are in inner region, these will require more energy. So that's why the energy required for beryllium will be higher and for boron it will be lower. So normal trend is that it should increase from left to right, but in this case, boron will have lower ionization enthalpy as compared to beryllium due to configuration, electronic configuration. If you see. Now, if I consider boron and carbon, in both the electron goes in 2p, so there will not be much difference. But in beryllium and boron, the orbital changed, and that's why the difference. Any confusion here?
So,
Yes.
we can't just directly say that as beryllium has a fully filled substrate, it is reluctant to lose an electron. That's the reason.
No, you need to write these 2 points that boron, the electron goes into p orbital. That's why there is greater shielding by inner 2s electrons. Second, in beryllium, the electrons are in the inner region. S orbital is smaller in the inner region, so it is difficult to remove the electron. These 2 points you have to write. Basically, your teacher will be looking for these 2 points only, not much explanation. So if you see here, that was just to explain that I took that much time. Otherwise, you have to write just 2 points. Okay, those 2 points are in beryllium, the electrons removed during the ionization in s electron, whereas electron removed during ionization of boron is a p electron. The penetration of 2s electron to the nucleus is more than that of 2p electrons, means 2s electrons are very close to nucleus. Hence 2p electrons of boron is more electron shielded from the nucleus by the inner core of electrons than the 2s electrons of beryllium. Inner core of the electrons means here 2s electron only, because we have only 2s electrons and 1s electron, but normally 1s electron providing shielding to both 1s, 2s and 2p. This is the statement you have to write. So therefore, it is easier to remove the 2p electron from boron compared to the removal of 2s electron from beryllium. Anything, any point not clear, let me know. Now, nitrogen versus oxygen within the same period, second period, okay? Lithium, beryllium, boron, carbon, nitrogen, oxygen, chlorine. Here we had exception between these two. Now again we have exception here also. And this is again due to electronic configuration, but reason is different. And if I write the electronic configuration, you will yourself probably get the answer. That why normally the ionization enthalpy is lowest here, highest here. It increases. But there is exception here. It has lower, and there is exception here as well. It has lower ionization enthalpy. The reason is that when I write the configuration, this is 7, this is 8. The configuration for this one will be 1s2, 2s2, 2p3. Configuration for oxygen will be 1s2, 2s2, 2p4. Now, if you see the outer electronic configuration in P, 3 electrons and 3 electrons as per Hund's rule of maximum multiplicity in P will occupy 1 orbital each. But in case of oxygen, there are 4 electrons, so this one will be paired. So there are two ways to explain this. As per Hund's rule of maximum multiplicity, this one will be a stable configuration. Why? Because it is half-filled configuration.
Yes.
Half-filled configuration is more stable than other configurations. Fully filled configuration is more stable than other configurations. So because this is more stable, this one, it will require more energy to remove the electron. It will not be willing to change its state. It will try to maintain its state. If it is more stable, it will try to maintain that state. That's why we are saying it is stable, because it is not willing to change. So it will resist the removal of electron. So you will just say, because as per Hund's rule of maximum multiplicity, it will have half-filled subshell. It will be more stable. It will require more energy to remove the electron. However, in this case, and this is another reason written as the answer. As we have 2 electrons in the same orbital, these will have higher inter-electronic repulsion. Inter-electronic repulsion. Now, if repulsion is higher, it will be easier to remove this electron. So two reasons you can mention both. Because it is more stable, it will require more energy or higher energy to remove the valence electron. Higher interelectronic repulsion means will require, or you can say due to higher interelectronic repulsion, it will have lower net effective charge. Net effective charge, I have told you, it is actually the force of attraction. Net force of attraction is low. Hence, requires less energy to remove valence electron. So oxygen requires less energy. So that's why lower the exception. Nitrogen is more stable. That's why it requires more energy. In oxygen, there is higher interelectronic repulsion also. That's why it further requires less energy. Any point not clear?
Sir, please can you show the previous slide once again?
This one.
Yes, sir. Okay, sir. Thank you.
Just go through the points. If any point is not clear, if you're not able to recall, just let me know. The same thing is written here. Half-filled configuration, Nernst rule of maximum multiplicity. So this is a stable state configuration. Yeah. And second is that 4 2p electrons in oxygen. So 2 electrons are in one orbital, so increased inter-electronic repulsion. Electron-electron repulsion means inter-electronic repulsion. Okay. So consequently, it is easier to remove the fourth 2p electron from oxygen than it is to remove one of the 3 2p electrons from nitrogen. Now the question, the first ionization enthalpy, you know first ionization enthalpy, we talked about it in previous class. The energy required to remove the valence electron from an atom which is in gaseous free ground state. Okay, isolated, free means isolated, isolated ground state, gaseous state. Moreover, one important concept is that when we say ionization enthalpy, electron gain enthalpy, whatever, these type of enthalpy, bond enthalpy, various types of enthalpy we will be talking about in chemical bonding chapter and in thermodynamics chapter as well, then these are for 1 mole. So if it is not written, you will always consider it is for 6.022 into 10 power 23 atoms we are talking about at a time. And each of those atoms is in isolated gaseous ground state. So if you see the unit of ionization enthalpy, it is kilojoule per mole, means we are talking about 1 mole. It is not just one atom. Otherwise, it will be written per atom there. If it is not written, it is always per mole. Now coming back to the question. The first ionization enthalpy of sodium, magnesium, silicon are given. Now predict whether the first ionization enthalpy for aluminum will be more close to 575 or 760. Now why the question is, because if you see the periodic table here, you have sodium, magnesium, aluminum, silicon. These 4 elements we are referring to in this question. For sodium, it is given 496, for magnesium 737, and for silicon 786, all in kilojoules per mole. The question is about aluminum, whether its ionization enthalpy should be close to 575 or 760. This is the question. Tell me the answer. Yes, Arjun. You have
Sir,
raised hand.
this question.
Hmm.
Sir, like we can also apply the previous concept. Like if we see the electronic configuration of sodium and magnesium, so the valence electrons are like they are embedded in the 3s orbital, but as we like reach to aluminum, the valence electron is in the 3p orbital, so the shielding effect by the inner levels of electron will increase and it will outweigh the effective nuclear charge, and so like uh, the ionization enthalpy of aluminium in its free gaseous atom will be much lower. So like it will be easy to remove an electron from aluminium. So its value, I think, must be closer than 2 to 575 kg per mole.
Correct, correct,
So may I?
correct. So that is correct explanation basically. So if you see the configuration of sodium, magnesium, aluminum, silicon, 11, 12, 13, 14. So electronic configuration 1s2, 2s2, 2p6, 3s1. 1s2, 2s2, 2p6, 3s2. 1s2, 2s2, 2p6, 3s2, 3p1. 1s2, 2s2, 2p6, 3s2, 3p2. So here again, from here to here, there is no significant difference because here it is going in S1, here in S2. So this is actually the similar
Only
one.
one is
Yes, only the difference of electron, but in the same subshell. So this is similar to what we discussed in case of lithium to beryllium and then beryllium to boron. So now from beryllium to boron, similarly here from magnesium to aluminum. Now there is difference because in previous case, electron goes in S, here it is going in P, and P is substantially larger than S.
yes.
So it means in P, there will be substantially higher shielding by inner core electrons, due to which net effective charge will decrease and it will be easier to remove. So it will be closer to 575, not 760. Theoretically, it looks like that because it is in increasing order. After 737, it should be 760, then 786. Rather, it is closer to 575 due to this reason. Similar to the concept, what we discussed, beryllium and boron. Same was the concept here, beryllium and boron. Okay. Now, electron gain enthalpy. Electron gain enthalpy again per mole. It will be. It will be energy change when an atom gains an electron. It means it is related to formation of ion, anion. Ionization enthalpy is related to formation of cation. So if I am talking about ionization enthalpy, I am removing the electron. So ionization enthalpy is related to formation of cation from its gaseous ground state neutral atom. But here in case of electron gain enthalpy, it is the energy change. And one more thing, the ionization enthalpy is always positive because it is formation of cation. You need to remove the electron. So ionization enthalpy is always positive. But when we talk about electron gain enthalpy is energy change. Okay. So that's why the keyword here is enthalpy change. It may be positive, it may be negative. So when an electron is added to neutral gaseous atom to convert it to a negative ion, then the enthalpy change accompanying the process is defined as electron gain enthalpy. It is denoted by delta EGH. EG stands for electron gain. Electron gain enthalpy provides a measure of the ease with which an atom adds an electron to form anion. Means, suppose you have chlorine. Chlorine has 17 electrons total, 2, 8, 7. So 2 electrons will be here, 8 electrons will be in second shell, and in third shell there are 7 electrons. 1, 2, 3, 4, 5, 6, 7. It means if it gains 1 electron, it will become very stable because it will attain noble gas configuration argon.
Yes,
It
sir.
gains 1 electron, 18
18.
argon configuration, noble gas configuration. It will be very stable. And I have told you that if something, any species becomes more stable, it means its energy will be less. And if energy is less, it means it will release energy. That much energy it will release. So in this case, energy is released. When energy is released, it is negative. In that case, it will have negative electron gain enthalpy. But suppose I am talking about carbon. Carbon has 6 electrons, means 2 electrons and then 4 electrons.
4.
Now, if it gains 1 electron, it is not going to achieve noble gas configuration or even stable state configuration. Okay. The problem is that because it is not achieving noble gas configuration, it is not willing to gain 1 electron. It means we will have to provide the energy to it. If we want to ensure that carbon gains an electron, we will have to force the electron into it. So that means we have to provide the energy. So in this case, electron gain enthalpy will be positive. But in case of normally in case of elements which are towards right, 16th, 17th, it is negative because if oxygen gains, for example, if we are talking about first ionization enthalpy, then only halogens, because by gaining just 1 electron, they will get converted to noble gas configuration. So first electron gain enthalpy will be negative for halogens. Second electron gain enthalpy might be negative, or overall electron gain enthalpy might be negative for chalcogens as well, because when they lose 2 electrons or they gain 2 electrons, they get noble gas configuration, oxygen, sulfur, etc. Okay, oxygen, sulfur, selenium, tellurium, polonium. Okay, all these are chalcogens. This is how electron gain enthalpy reaction is represented. There is free atom, it gains an electron, gets converted into energy. The energy change in this case is known as electron gain enthalpy. Depending on the element, the process of adding it can be endothermic or exothermic. So it will be endothermic if it requires energy, okay, requires energy or absorbs energy. It will be exothermic if energy is released. For example, for halogens, energy will be released when 1 electron is gained. So for many elements, and energy is released, it means it is negative in that case. For example, as I told you, group 17 elements, the halogens, they have very high negative electron gain enthalpies because they can attain noble gas electronic configuration by picking up 1 electron. On the other hand, noble gases have large positive electron gain enthalpies because they already have a stable state configuration. So if I consider neon, neon has 10 electrons, it will have 2, 8. So it will not be willing to gain electron because it already has a stable state configuration. So we will have to force an electron into it. And when we force an electron, we will have to provide the energy. It means it will be positive. So noble gases will have very high electron gain enthalpy. These will be used to answer the question. So memorize these things. We will be doing question which will require this knowledge to identify the elements. You will be given a few enthalpies, electron gain enthalpy, ionization enthalpy, etc. And on that basis, you will be asked that which one can be magnesium, which one can be the other one. Okay, for example. Electron gain enthalpies have large negative values towards the upper right of the periodic table preceding the noble gases. So most negative, however, there is exception, okay, with exception. So in this region, most negative, and in this region, very high positive. Okay? Now remember, both of these regions will have high positive electron gain. The reason is that here, if lithium, for example, loses one electron, then yes, it will be easier. It will gain noble gas configuration, helium configuration. So lithium has 1s2, 2s1, or you can say 2, 1 configuration. So if it loses this one, it will attain helium configuration. But if you want to get one electron into lithium, then there will be higher interelectronic repulsion. It will not be willing to gain one electron. So means you will have to force the electron into it. So high positive electron gain enthalpy on left side and in noble gas. So again, here also the electron gain enthalpy is less systematic than ionization enthalpy, means there are exceptions. So as a general rule, electron gain enthalpy becomes more negative with increase in atomic number across a period. So it becomes more negative. What it means? It means the magnitude of the energy released increases. Negative means just to say that energy is being released. Negative does not mean that energy is decreased. Negative means the energy is being released. So it means the magnitude is increasing. Magnitude of electron gain enthalpy increases. Okay? Or you can say absolute value, because absolute value will not contain the sign. Absolute value of electron gain enthalpy increases across the period. Negative sign just shows that this energy is released. Now, why it happens? It happens because the size of the atom decreases across the period. So if it decreases, if electron enters here, for example, I am explaining from here. If one electron enters here, there will be higher interelectronic repulsion in this case, and there will be high interelectronic repulsion in this case also. So higher interelectronic repulsion will be in both cases. But what prevails and what outweighs is the force of attraction when electron enters the atom. Here, this electron is closer to nucleus. The electron which enters here is farther from nucleus. So because this one is closer to nucleus, it is attracted with greater force. means more stable. More stable means higher energy released. All these steps should be clear. I am repeating again and again. More stable means it will have less energy. It will have less energy means the rest of the energy will be released in the atmosphere, in the surroundings. So higher energy released means higher electron gain enthalpy. So that is the reason. The effective nuclear charge increases from left to right across a period, and consequently it will be easier to add an electron to a smaller atom since the added electron on an average would be closer to the positively charged nucleus. So if size is small, the valence shell will be smaller. The electron will enter the valence shell and it will be.
So, sir, the enthalpy would increase.
Hmm? Come again.
So the electron gain enthalpy will increase if we move from left to right.
Yes, it will increase. It will be negative, but it will increase. The energy released will be higher. So across the period, the electron gain enthalpy increases. Negative electron gain enthalpy increases. But if we talk about down the group, the incoming electron is far away from the nucleus. So incoming electron here will be closer to the nucleus. But incoming electron here will be far away from the nucleus. It means the closer one will be tightly bonded. Okay, will be attracted more. Means it will be more stable. I'm talking about down the group only. So down the group, less energy will be released. Less stable. Less energy released. So I'm talking about in terms of negative electron gain enthalpy only. Okay, electron gain enthalpy will be positive if we are talking about extreme left or noble gases. In that case, we will have to provide energy to get the electron into the atom. When I am saying less energy release means the negative value of the electron gain enthalpy will be less. So how you will remember it? You will remember it like if this is the periodic table, electron gain enthalpy except the noble gas configuration. I'm talking about up to here. Okay. Here it will be most negative. Okay. And here it will be most positive. That's why I'm talking about in terms of negative. So electron gain enthalpy generally becomes less negative as we go down the group. Less negative can be in case of left elements. It will rather become positive. So in this region, it will be rather positive. Okay, positive. The only thing will be here, it will be less positive. Here it will be more positive.
Sir, how
Towards
does it
right,
vary with magnitude?
just
So like this positive and negative.
yes, I'm coming to that. Here it will be most negative. Here it will be least negative, but it will be negative towards right, except noble gas, and towards left, it will be positive. Magnitude wise, that's what I'm saying. Okay. if you consider, say, the number line, what you do? You say it is 0, and we have -10, -9, -5, -1, and +1, +5, +9, +10. On the number line, anything towards left is less than anything towards right. Okay, so here this is less, this is towards right. So if I compare these two, 10 and -10, -9, -9 is greater than -10. So whatever is at the right side is greater. Okay. Now, in this case, what I am saying, in periodic table, here in this region, energy will be released when it gains electron. So when energy is released, I am talking about negative sign because energy is released. So here more energy will be released. Don't get confused. That's why I have drawn this line. Don't get confused with these values, because here we are talking about their magnitude in terms of signs. What I am talking about here sign represents only the direction of energy, not the magnitude. So if I am saying more energy here is released, it means, say, -100 units. Here I am saying less energy released. Here I am saying -50. So if you compare it with number line, you will say -100 is less than -50, what I am talking about. So I am not talking
Yes,
about
sir.
with sign. Negative is just for direction. You will consider -100 as 100 release and 100 units energy released. Here -50 you will consider 50 units released. Minus stays released. Okay. But if I am talking about in this region, I am saying here less positive, say +25, and here more positive, say +75. So +25 means 25 units absorbed. 75 means 75 units absorbed. That's what I'm saying. So don't get confused negative sign with the number line. On the number line, right side is greater than left side. But here I am talking about negative is just an indication of the direction of energy, not its magnitude. Is that clear?
Yes, sir.
Yes.
So, however, electron gain enthalpy of oxygen and fluorine, and this is where questions will appear. Okay, oxygen and fluorine, we have exception here. Exception with what? Exception with the group. Means we said that in this region, the electron gain enthalpy will be most negative. So if we are saying it is most negative, and we said here it was most positive, then the sequence is something like this. And if it is something like this, fluorine should have most negative electron gain enthalpy. From most positive to most negative, fluorine should have most negative electron gain enthalpy, but that's not the case. Okay, again in this group, we say across, sorry, down the group, the electron gain enthalpy decreases. So fluorine should have maximum. In this group, we say down the group, electron gain enthalpy decreases. It means oxygen should have most negative electron gain enthalpy, but that is not the case. The reason is when we consider fluorine, chlorine, bromine, iodine, normally, if you remember, I'm going back to this one. We said that down the group, the electron gain enthalpy becomes less negative. Less negative means just the sign is negative. Otherwise, we are saying it decreases. Minus 100 to say minus 50. So minus sign just says releasing energy. It means it decreases. So if it decreases at the top, it should be maximum because negative just indicates it is released. And it should be minimum here, energy released. But it is not the case. Chlorine does not have most negative electron gain enthalpy. And why? The reason is when electron, in this case, when they gain the electron, they attain noble gas configuration, and that's why a huge amount of energy is released. They become stable. In case of fluorine, fluorine is exceptionally a small atom. This is something, if you remember, I talked about in previous class as well. Exceptionally small atom means smaller than its theoretical value. In reality, its size is less than its theoretical value. So when it gains one electron, it is second shell. So 9, 17. 2 electrons here, 7 electrons here. When it gains an electron, there is significantly higher interelectronic repulsion. Very high interelectronic repulsion. You remember I gave you an example in the last class that if you are in a very small room and someone says that, okay, can I stay with you? You will say, no, I don't have space here. We are already 3 here. We don't have much space here. But if you are in a hall, you will say, okay, you can occupy the space. There's ample space. You can be there. So that is the case here. In fluorine, there is very less space already. So the new electron experiences very high interelectronic repulsion after it has entered the atom. So due to that, the net force of attraction decreases. Higher interelectronic repulsion means net force of attraction decreases. So not as stable as expected. Practically, it is not as stable as expected theoretically. But in case of chlorine, chlorine is third shell, and third shell is significantly larger. And it has again 7 electrons only. Second shell in fluorine, second shell was very small, and there were 7 electrons. In chlorine, third shell, again only 7 electrons. There is huge space. So the incoming electron has very small interelectronic repulsion. Means force of attraction outweighs interelectronic repulsion here. Yeah. The rather you say noble gas configuration outweighs interelectronic repulsion. However, here, due to higher interelectronic repulsion, force of attraction is less. It is less stable. Less amount of energy is released. So chlorine is actually the compound element which has higher electron gain enthalpy. Similarly, oxygen and sulfur. Oxygen is very small, so sulfur has higher electron gain enthalpy, negative, higher negative electron gain enthalpy. Let me know if anything is not clear.
No, sir.
Sir, just now you were discussing about this side. Sir, the negative side, do the rules hold same for the positive side as well? At the left side of the periodic table.
Yes. Basically, in that case, it is not going to attain noble gas configuration. So we will not be talking about in those terms. But
Yes.
if we talk about in terms of whether it is away from the nucleus and it is closer to nucleus, those concepts will be
Yes.
similar.
And sir, what direction does positive sign indicate, sir?
Positive sign indicates that we need to provide the energy to the atom so that it
Yes, sir.
gains.
So as it will gain the at electrons, then it will try to become more stable, sir.
No, that is something I will come to later on. Okay. But the electropositive elements which are towards the left, okay, towards the left,
Yes.
the elements we have, these are electropositive elements here. If
Yes.
we give them energy and they even gain the electron, those will not be stable. Okay, those might act as intermediates, but those will
Yes.
not be.
Okay, sir.
So this is because when an electron is added to oxygen or fluorine, the added electron goes to the smaller n equals to 2 quantum level and suffers significant repulsion from the other electrons present in this level. However, for n equals to 3, sulfur and chlorine are in third shell. The added electron occupies a larger region of space and interelectronic repulsion is much less. That's why this is the exception here, that electron gain enthalpies of oxygen and fluorine are less negative than sulfur and chlorine respectively. So this region you need to remember exception in these four. So basically one exception between fluorine and chlorine and similar between oxygen and sulfur. Now the question, which of the following will have the most negative electron gain enthalpy and which the least negative electron gain enthalpy? Tell me the answer. You can raise your hands if you want to answer on mic. Only one hand raised till now. Okay, Kavish, correct answer. Okay, because Yash has raised hand. Yes, Yash, tell me the answer.
Sir, I think so. Chlorine will have the most negative electron enthalpy.
Hmm. And most and
And
least negative.
I think so. Phosphorus will have least.
Hmm?
Sir, I
Which
think
one?
phosphorus will have least.
Okay, right, correct answer. We just talked about that most negative region is here, but there is an exception. Theoretically, fluorine should have most negative electron gain enthalpy, but actually chlorine has, because fluorine has higher interelectronic repulsion. So chlorine has most negative electron gain enthalpy in the periodic table. Now, the electron gain enthalpy, when we talk about across the period, so it is like this. Okay. From phosphorus, sulfur, chlorine, the electron gain enthalpy will become more negative. Okay. So in this direction, more negative. And we know by exception between fluorine and chlorine, chlorine is more negative electron gain enthalpy than fluorine. So chlorine will have most negative electron gain enthalpy. Otherwise, it would have been fluorine. Okay? Because by trend, more negative
So what will be the reason?
electron gain enthalpy and down the group, less negative. It means more negative if I change the direction. But so I say phosphorus, sulfur, chlorine. By this rule, chlorine is most electronegative. But by this rule, we might say fluorine should have most electronegative because moving upward, fluorine should have most electronegative. But due to exception, because fluorine has higher interelectronic repulsion, we have just talked about fluorine has higher electron gain enthalpy, negative electron gain enthalpy than fluorine. So answer is fluorine. Now this rule is straightforward. More negative electron gain enthalpy towards right side, it means fluorine will have least negative electron gain enthalpy. It is towards left, so least negative. Fluorine will have most negative. Let me know if there is any confusion. From
So please
phosphorus
explain the
sulfur.
reason.
Come again.
Please explain the reason once again.
The reason I am saying for phosphorus sulfur chlorine, is that clear or not? Phosphorus
Yes, so
sulfur
that's
chlorine, the electron gain enthalpy becomes more negative when we move from left to right. So from that, chlorine, phosphorus will have least negative in this region only. I am talking about. Okay, I am talking about
Okay,
just
sir.
in this region. Chlorine will have least negative, and chlorine will have most negative for these three only. Now, if we consider the group, in group normally, when we move down the group, it becomes less negative. But this is exception here. Between fluorine and chlorine, we just talked about the exception. This exception we talked about. Because in fluorine, fluorine is very small atom. When electron enters, it is not very stable. It is not very stable. Not so much energy is released. Rather, more energy is released in chlorine. So chlorine is most electronegative. But suppose we consider uh, chlorine, bromine, iodine, etc. Then here in this case, the trend will be more negative electron gain enthalpy. But just between fluorine and chlorine, it is reverse. Chlorine will have more negative electron gain enthalpy than fluorine. So exception should be clear here. Then you will be able to answer.